And then the next thing we ask is what? What is the hardness? Now, where is the hardness in this diagram? Anyone? 0.1, 0.2, or 0.3? I hope you guys are there. Yes? Hello?
I think 0.1.
Yeah. So when we ask about hardness, this is what we're asking. Yes or no? It's 0.1. Question for you guys.
Yes.
Is this information useful?
Not really.
Absolutely useless up to today. Okay, I recently did a consulting contract recently. Same thing, Eugene. We have this material, and this is our hardness. Graduates from McMaster will know as a manufacturing engineer, this information is as good as useless. Useless. Asking about hardness. Absolutely. Why? Because at hardness, what do we know? We only know at this point. Any useful? No. We want to know this part. We want to know about this behavior over here. And this behavior, the gradient, is controlled, right? Is controlled by who? By V and N. Right? It's controlled by your strain hardening coefficient. It's controlled by your N, which is your strain hardening index. So for the past, like, how many long years, right? We've been asking the wrong question, and we realize that, oh, crap, it is difficult. Right? And I'll give you examples later on. Something that is soft, when you deform, can become harder. I repeat again. Something that is soft, okay, soft means what? 100 megapascal, for example, right? It can be more difficult to deform when compared to another material that has a hardness of 600 megapascal. How could you explain that? It's because of the hardness, the value that we ask regarding hardness is useless. What we want to find out in manufacturing is what is your what? B and N. Okay,
So,
I'm not.
So
yes.
Usually in the drawings, when they ask for material, they ask for like steel, crest steel 4335, hardness HRC 33 to 35. So
yeah. So these people that do all this drawing, they are what? They're design engineers, right? Are they manufacturing engineers?
Well, where I work, we got drawings from Boeing, so they usually have pretty good design engineers.
No, Boeing don't care what you do. They just tell me, you give me the tolerance and the shape, I will pay you. Do they really care? They want you to have the knowledge to be able to dictate how B and N will affect your manufacturing. Listen, this is where in Canada we have to rely on knowledge-based technology. Okay, I'm going to impart you.
So far, all the drawings that I've been seeing from Boeing or from Bombardier, even Airbus, they all call for a material in the same way. Like we need steel, craft steel, then steel specification, then the hardness they require.
Yeah, useless, right?
Buying the material this way from the mills. Yeah.
This is very good point. Okay, you just brought up a very good point. So you will buy the material, right, from what Boeing requests. Am I right?
Yeah.
No. I will give you examples later on that you buy the material that is softer, you bend it to shape, then you make it harder, and then you send it back to Boeing or Bombardier.
No, they have like the requirement what the raw material you can purchase, and then they have a hardness requirement what the hardness should be after the machining.
Yes,
like after machining you do a heat treatment, right?
Exactly, is the after process. Okay, before that, what are you going to use? A lot of times, industry are very blind by this. If my customer order fish and chip, order a fillet of fish, I have to buy fish. That is food, sunshine. In science-based manufacturing, if Boeing or whoever asks for a material that is 60 Rockwell C when I deliver to Boeing, when I buy the raw material, it does not need to be 60 rod LC. Do you know how difficult to deform 60 rod LC?
No, yeah, but I'm saying for raw material also they're providing you specification what you can buy. So you only
Yeah,
have to
but
buy. Yeah.
that's one company that has a very good engineering team that can tell you those things.
No,
Yeah.
yeah, I know, but I'm just saying,
Listen,
like, all the
They
drawings that I've seen so far.
they are doing that because they want to limit you to the type of supplier that you could use. And I'll be very surprised. Okay, what is specified is not hardness. What is more specified is the microstructure, chemical composition. Okay, and the trade name of the material. Hardness is you can adjust before delivery. Okay, if you can't, if they specify something that is 90 rod LC, don't take the contract. Walk away. You go bankrupt. Okay, so that's where you have to embrace this technology. I'll give you real case study later on that I've implemented exactly the same problem. Okay, this is what my customer want. I'm going to order the material at 65 rod LC. After that, crap, I can't
Yeah.
produce anything. Right?
For
Okay.
aluminum, I see we heat treat to O condition, then work it. Like we can order it any hardness, then we heat treat it to O condition, then we can work it. Yeah.
Yep. Aluminum is straightforward because aluminum is more easy to deform. Okay, so it's not that complicated. You just need to meet your customer requirement. But if your customer requires something that's really hard, why they require something that's hard? A design engineer will design something very rigid. A manufacturing engineer will say that this is too hard for me to what? Deform. That's why there's a constant battle between manufacturing engineer and design engineer every day. That's the reason, okay? But with knowledge like this, we're going to solve their problem, okay? We don't care what they are. Now, let's look at the deformation pattern, okay? So this is in the plastic region, okay? So this is the in the plastic region, and we are only going to look at the up to the ultimate strength, okay? Up to the ultimate strength. I like this class, okay? A lot of you have experience in the industry, and hopefully after this class, you guys will be more motivated to think in terms of mechanics and material science also, okay? So in region 1, okay, the deformation pattern will look like. So we put it through tensile. This is our load, okay? And then when it reaches 2, what happens? It becomes what? Longer. You don't see anything change at all, okay? Except the length. So you can see I deliberately draw a longer length. And then at number 3, right, once you see the U strength, it's still the same. It just become longer. Okay. Okay, so the 1, 2, and 3 correspond to the 1, 2, and 3 over here. Okay, so now is 8 o'clock. What I propose that we go for a 15 minutes break. Okay, we go for a 15 minutes break, then we come back. Okay, so go for a 15 minutes break. We come back at 8:15.